Okay, now let's talk about priors. One of the most important and sometimes even controversial parts of Bayesian statistics. Now, a prior is your belief or assumption about something before actually seeing the current data. This belief can come from past experience or expert knowledge or even historical data that you looked up or that you learned. And these all play a role in Bayesian analyses because it starts with this prior and then updates the prior using new evidence, and this results in your posterior belief. So there are different types of priors depending on how much information they contain. There's informative priors, reflect strong past knowledge. As an example, a doctor might know a condition appears in 10% of similar cases. And there's also weakly informative priors, which are more like guardrails, and they guide the model a little bit, but don't overwhelm the data. And then there's non-informative priors, which are purposely vague. They assume nothing or very little and really just let the data speak for itself. So choosing the right type of prior depends on the context and how much you already know that is going on. So you might not realize it, but we use priors all the time in real life. A doctor might expect a flu diagnosis during flu season, and that's an informative prior. Or an investor may rely on recent market vitality to guide his or her decision, another form of prior knowledge. And then even toddlers learn language, and they start with the expectations about sounds and shapes. As you can see, our brains are wired to update beliefs using past experience, and that is Bayesian thinking at work. Now, the influence of a prior depends on how much data you actually have. When data is limited, your prior can heavily influence the posterior. But when you have lots of data, the likelihood dominates and the prior's role fades. That's why priors are powerful tools early on, because especially in medicine, early stage research or small studies can really benefit from Bayesian statistics. Bayesian thinking balances belief and evidence, and the more data you get, the more objective your model becomes. Now, next up, we'll explore the likelihood, which is the other key part of Bayes' theorem. You'll learn how data gets folded into the equation and how the likelihood works with the prior to produce the posterior. We'll keep things simple and even example driven as always.